the silent darkness of space. There are worlds we cannot see, at least not at first glance. For centuries, distant planets were only whispers, tiny shadows and barely perceptible fluctuations in starlight. But today, new methods and technologies allow us to see these faraway worlds. Now, we're not just finding exoplanets. We're beginning to read their skies. In the glow of alien atmospheres, astronomers search for clues to untold stories. How do we uncover the secrets of a world located many light years away? We look into its atmosphere. The thin veil of gas surrounding the planet is not just air. It's a cosmic journal. Each molecule a separate chapter. The atmosphere can reveal the planet's biography, its birth, geology, weather, even hints of life or the absence of it. Reading it isn't easy, but if done right, it can tell us whether a planet is a scorched gas giant swept by winds or a tranquil water world, and whether something strange might be forming in its clouds. Each atmosphere is unique. It carries the signature of the planet's composition and history. Carbon dioxide whispers of ancient volcanoes. Water vapor hints at rain and oceans. Methane might be exhaled by life or produced by geological processes. To a trained eye, the atmosphere is a story written in chemical script. But how do we read that story from so far away? The key is light. Although we can't touch these distant worlds, their light still reaches us. Encoded in that light is the fingerprint of their atmospheres. Using a technique called spectroscopy, scientists split the light of stars and planets into a rainbow, search for dark or bright lines, chemical fingerprints that show what gases are present. One of these methods is transit spectroscopy. When an exoplanet passes in front of its star, transit, a tiny portion of the starlight filters through the planet's atmospheric shell. By comparing the star's spectrum before, during, and after the transit, we can detect extra absorption, a specific wavelengths caused by gases in the planet's air. That first breakthrough came in 2001, when the Hubble Space Telescope captured such a transit. As the giant planet HD 209458b eclipsed its star, Hubble detected a distinctive fingerprint: sodium gas in the planet's atmosphere. It was the first chemical confirmation that yes, indeed, exoplanets have atmospheres we can detect. As exoplanet formation pioneer Alan Boss remarked at the time, the first detection of the atmosphere of an extrasolar planet means we've entered into a new phase in the era of planet discovery and characterization. Transit spectroscopy opened the gates to this new world. Using Hubble and other telescopes, scientists began routinely scanning alien skies. They found sodium on that first hot Jupiter, then water vapor on others, followed by hints of methane and carbon monoxide. Each new detection was like learning a new word in an alien language. By the 2010s, we learned that some giant exoplanets have cloudy, water-rich atmospheres, while others are surprisingly clear and dry. In one case, Hubble even detected water vapor in the atmosphere of a small temperate exoplanet called K2-18b. Marking the first time water was observed on a world located in its star's habitable zone. K2-18b is a super-Earth with a mass about 8 times that of Earth. its wet skies caused excitement around the globe. Some scientists argue it's more of a mini Neptune than an Earth-like world with a thick hydrogen envelope. The presence of water proved to be a decisive factor. But transits aren't the only method. Another approach is direct imaging using coronagraphs. Instead of watching a planet's effect on a star's light, we try to see the planet itself. This is insanely difficult since stars outshine planets by millions or even billions of times. But with special masks called coronagraphs, or even separate space instruments that block out a star's glare, telescopes can directly capture the faint glow of a few large young planets. In 2008, a stunning image emerged. 4 tiny dots of light orbiting a distant star, HR 8799, the first family portrait of an exoplanetary system. For years, these 4 giant planets, each several times more massive than Jupiter, were observed circling their star, giving us a window into the architecture of another solar system. At first, these kinds of direct images only showed the positions and orbits of the planets. But now we can also analyze their light. In spring 2025, the James Webb Space Telescope produced the clearest infrared images of HR 8799 to date. By dispersing the planet's own infrared glow, JWST revealed that these 4 giants are enriched with heavy elements like carbon and oxygen, evidenced by strong carbon dioxide signatures in their spectrum. These suggest they likely formed through slow gas accretion onto solid cores, similar to Jupiter in our system. By spotting these strong carbon dioxide features, we've shown there's a sizable fraction of heavier elements in the planet's atmospheres, explains astronomer William Balmer, whose team worked on the images. With direct imaging spectroscopy, we're not just seeing those planets, we're tasting their air, learning how worlds are built, piece by piece. There's also a third method, akin to building a thermal portrait of the planet. When a planet moves beyond its star in a process known as secondary eclipse, you can measure the drop in total infrared emission. By measuring this dip at various wavelengths, astronomers map the temperature distribution on the planet's day side, essentially creating a basic weather map of a distant world. This method is known as eclipse mapping or phase curve mapping. It's astonishing. With precise timing and instruments like JWST, scientists can determine whether one side of the planet is hotter or colder, possibly indicating cloud cover or winds that distribute heat. In one of the earliest famous attempts, the Spitzer Space Telescope mapped the scorching day side of exoplanet HD 189733b, finding a giant hotspot pushed by fierce winds. Today, eclipse mapping is advanced to reveal even finer details, like potential contrasts between continents and oceans on future Earth-like targets. Piece by piece, these methods, transits, imaging, eclipse mapping, and more, allow us to scan the atmospheres of distant worlds. The data may appear as lines on a graph or barely perceptible shifts in brightness, but to scientists, they're profound revelations. With each spectrum, turn a point of light into a world with personality. Clouds or haze, calm skies or poisonous mists, tranquil seas or erupting volcanoes hidden below. And the revolution in what's possible has only just begun. So where do we stand today? Over the past 2 decades, astronomers have compiled an entire scrapbook of atmospheric discoveries. One significant event followed another, each revealing something new about these distant worlds. In 2001, HD 209458b, the original hot Jupiter, revealed the presence of sodium in its atmosphere, the first atmospheric fingerprint of an exoplanet in history. The era of remote probing of alien skies had begun. By 2007, the Hubble and Spitzer telescopes had detected water vapor on the scorched planet HD 189733b, proving that even hot gas giants could contain water in their air. Astronomers began speaking of clouds and haze on worlds heated to white-hot temperatures. In 2013, using a ground-based telescope equipped with a super-precise spectrograph, researchers detected carbon monoxide winds rushing through HD 209458b's atmosphere at thousands of miles per hour, the first direct measurement of weather on an exoplanet. In 2018, Hubble data showed water vapor in the atmosphere of WASP 39b, and a year later, it famously discovered water on K1218b, a smaller planet in the habitable zone. These were tantalizing hints that even beyond our solar system, water, the elixir of life, might be fairly common in the skies of other worlds. Each discovery added a new ingredient into our cosmic recipe book. We've detected sodium, potassium, water, carbon monoxide, methane, hydrogen, helium, and more. For a while, the list was dominated by elements that our older instruments could detect, and typically those easier to spot on large hot planets. But then came a turning point, the arrival of the James Webb Space Telescope. Launched in 2021 and fully operational by 2022, JWST began closely examining the atmospheres of exoplanets. In its first months, it targeted WASP 39b, that same puffy hot Saturn where Hubble had seen water, and found a veritable treasure trove of chemicals in its skies. For the first time in history, we saw a clear, unmistakable signal of carbon dioxide in an exoplanet's atmosphere, a peak in the spectrum exactly where a CO2 fingerprint should be. Astronomers rejoiced. CO2 is not only a common planetary gas, but also crucial for understanding a planet's history. It's released by both volcanoes and life forms. James Webb did not stop there. As more data arrived, WASP 39b also revealed sodium, potassium, water vapor, carbon monoxide, and even a surprise, sulfur dioxide. Sulfur dioxide on a distant planet was quite the revelation. It suggested the presence of photochemistry, chemical reactions triggered by starlight, much like sunlight creates ozone in the Earth's atmosphere. In other words, we were seeing an alien atmosphere reacting to its star in real time, producing new molecules. The discovery of photochemistry in the atmosphere of a hot Jupiter exoplanet is important, opening new avenues of investigation, said Professor Natalie Betelgeuse, who leads the JWST team studying WASP 39b. For scientists, this was like reading not just a list of planets' chemicals, but witnessing an active process, a dynamic story unfolding in those clouds. James Webb provided the full chemical composition of the planet, revealing clues about its formation. For example, a high oxygen-to-carbon ratio suggests it formed far from its star, accumulating icy materials. But JWST's capabilities go even further. It has begun sniffing the air of Earth-sized worlds. In the TRAPPIST-1 system, just 39 light-years away, 7 rocky planets orbit an ultra-cool star. These are prime targets for seeking atmospheres like Earth's. 2023, James Webb observed the innermost planet, TRAPPIST-1b, and the result? Most likely there's no atmosphere at all. The planet seems to be a bare, scorched rock. That result is a bit disappointing, since TRAPPIST-1b is too close to its star to be habitable. It was a triumph of detection. James Webb was able to directly measure the planet's heat and found that the day side is so hot that any thick atmosphere would have redistributed the heat or shown an infrared absorption signature, but none was seen. Everything suggests that TRAPPIST-1b is airless and scorched by stellar radiation. However, its siblings, especially TRAPPIST-1e, F, and G, are cooler and potentially habitable and are next in line for study. Do they have atmospheres? Well, we're on the edge of our seats to find out. Our catalog of alien atmospheres now includes hot Jupiters, warm Neptunes, mini-Neptunes, and a few possible super-Earths. We found planets with iron rain, where it's so hot that metals evaporate and condense into droplets at night. We found others with global cloud decks of sand or sulfur. We've measured winds, discovered hazes, and even seen the fingerprints of atoms like titanium and sodium escaping into space. But when we decode an exoplanet's atmosphere, what exactly are we looking for? Some gases act as clues to planetary processes. Take carbon dioxide, for example. CO2 can build up from volcanoes belching carbon from a planet's interior or from a thriving biosphere. And on Earth, CO2 is always present thanks to both volcanoes and life, including us. Finding CO2 in a distant world's atmosphere tells us there's active chemical processes, but it's not proof of life by itself. Venus has a lot of CO2, and nothing's alive. Context matters. Or take water vapor, H2O. If we detect water in a planet's air, it might mean clouds, or even rain. It's a clue that temperatures may allow liquid water, or at least high in the atmosphere. Water vapor was one of the first molecules ever found on exoplanets. It remains one of the most common. On giant planets, it tells us about the formation process, like how much oxygen is present. On small planets, it's a key piece of the habitability puzzle. But again, caution. Even Jupiter has water deep in its layers. Water doesn't mean habitability. Methane is more intriguing. On Earth, most methane comes from life. Microbes, and yes, cows, with a bit from geology. In an oxygen-rich atmosphere, methane shouldn't last long as it reacts quickly. So detecting both methane and oxygen in an exoplanet's atmosphere would be a thrilling hint of biology, because something must be replenishing the methane against the odds. Scientists dream of this combination, but we haven't seen it yet. Still, we found methane on several giant exoplanets. Usually it's found on the cooler gas giants, helping confirm, for example, that the young planet HR 8799b has an atmosphere similar to that, say, of a young T-type brown dwarf. Our list also includes oxygen and its sibling ozone. Free oxygen is hard to build up unless something's making it. It likes to bond with other elements. On Earth, we have abundant O2, thanks to photosynthesis. We haven't yet detected oxygen on any exoplanet yet. That's challenging, even for JWST. But upcoming missions will focus on spotting it on nearby Earth-like planets. Still, a dash of realism. Even oxygen alone can't be taken as undeniable proof of life. In 1990, when NASA's Galileo spacecraft conducted a clever experiment by looking at Earth as if it were an exoplanet, it easily detected oxygen and even methane, pointing to the presence of life. But researchers warn that in theory, a planet could build up oxygen through non-biological means, like in a greenhouse effect, where water is split and hydrogen escapes. One Earth-based study concluded that even an oxygen-rich atmosphere alone is not a slam-dunk evidence of life. we'd want to see it alongside other signs like methane, or maybe seasonal change, or odd chemicals like chlorophyll breakdown products, which would offer a richer set of indicators. Even sulfur compounds like sulfur dioxide or hydrogen sulfide can be telling. In the volcanic world, SO2 might come from eruptions. On the aforementioned WASP-39b, the unexpected SO2 was a sign of active photochemistry, reactions happening under the influence of a star, showing the atmosphere isn't inert, but a living chemical reactor. It's an alien version of smog, the product of starlight interacting with gas. The conclusion is this: not a single molecule says, hey, there's life here. It's all about patterns and context. Scientists speak of searching for biosignatures, which often means detecting pairs or trios of gases that shouldn't coexist unless something like life is replenishing one. One such pair is O2 and CH4. Another may be N2O, laughing gas, byproduct of microorganisms alongside O2. On the other hand, geosignatures can tell us about the geological activity of the planet. For instance, SO2 plus water may indicate volcanic stream, while large amounts of CO along with H2 might suggest a world that has undergone intense heating. As we collect more and more atmospheric profiles, we begin to learn which combinations scream dead planet and which ones whisper maybe, just maybe. Meanwhile, as JWST continues to amaze us, astronomers are preparing the next generation of planet hunters, which will expand our atmospheric survey. Leading the way is Ariel, developed by the European Space Agency and set for launch in 2029. Ariel has a singular goal: to study the atmosphere of around 1,000 exoplanets. It will focus on warm and hot planets, from scorched rocky worlds to sub-Neptunes and gas giants, to understand what their skies are made of. Using specialized spectrometers, the spacecraft will systematically observe one planet after another as they transit their stars, building the first large-scale chemical catalog of exoplanet atmospheres. Scientists like Professor Giovanna Tonetti, project's principal investigator, often calls this a cosmic population census, aimed at answering crucial questions. How do planets with different chemistries form and evolve? Why do some have abundant water and carbon dioxide while others have almost none? Around the same time, NASA will launch the Nancy Grace Roman Space Telescope. The telescope's main job will be capturing wide-field images of the cosmos. But on board, it will carry a revolutionary instrument, a complex coronagraph. This device will be the most advanced of its kind ever sent into space. In essence, Roman will attempt something akin to magic, directly imaging planets that are tens of millions of times fainter than their stars, and even capturing spectra from some of them. For the first time, we may see exoplanets in visible light, and perhaps even observe seasons or clouds on some of them. This is a crucial step toward future missions that may one day photograph another Earth. And back on Earth, work continues on building giant telescopes, such as the extremely large telescope in Chile, with its 128-foot mirror. It will use cutting-edge optics and high-resolution spectroscopy to study atmospheric molecules, allowing for the detection of biosignatures on Earth-sized planets orbiting nearby stars. Looking further ahead into the 2040s, projects like NASA's Habitable Worlds Observatory, the planned successor to JWST, will be aimed at directly imaging Earth-like exoplanets in search of faint signs of life in their skies. Each new mission builds on the legacy of the ones before it, bringing us closer to the grand prize. This is a relay race of innovation, Hubble gave us our first hints. Spitzer and ground-based telescopes added new clues. JWST is revealing a rich diversity of atmospheres. Ariel will perform further research, and Roman will pioneer new techniques. With each new eye observing the sky, the hidden faces of these distant worlds become a little bit clearer. Tonight, as we gaze at the sky, perhaps one of those stars is home to a planet with a sky very much like our own. We haven't found it yet, but we are getting closer. With each new telescope, each observed transit, with each captured spectrum, we improve our ability to recognize the markers of the known and the unknown. Perhaps the first detected atmosphere of an Earth-like exoplanet will surprise us. Maybe it will show a smudge of pollution or an unexpected balance of gases that challenges our definitions of life. Or maybe, one quiet day, the telescope will reveal an unmistakably familiar picture. A mix of nitrogen, oxygen, water vapor, and reactive methane, all in delicate balance. And when that day comes, when the atmosphere of an exoplanet whispers, "This place feels like home," how will we respond? The answer lies out there, in starlight filtering through alien skies. An answer we're finally starting to understand.